Yesterday, I introduced an equation to you. It said F is equal to ILB. This equation was used to find the magnetic force acting on a wire that carries a current, right? We called it yesterday a current carrying conductor, when it was exposed to an external magnetic field. Today we're going to use that equation along with some data in order to find the value of a magnetic field in a magnet that we're going to use in this experiment. Here's how it's going to work. There's actually going to be two parts to this experiment, two mini experiments in one. Part one is going to involve an apparatus that you see up on the board here right now. There's a power supply right here. This is going to be what generates current. It's going to be what produces the current or what supplies the current to the rest of the apparatus. That's our power supply. Over here, we've got what's called a current balance apparatus. Attached to that current balance apparatus is a little thing that plugs in and can be unplugged. It's a little printed circuit, actually, that has a wire. That wire, okay, will eventually carry an electric current and be placed in between the two poles of this magnet that you see right there, a permanent magnet. So you got a wire in between the two poles of this permanent magnet here, a north pole and a south pole. Now this power supply is going to, once we flip it on, is going to send electric current from one end through the wire, through one of the arms of the current balance apparatus, down through the printed circuit, down through the wire that's actually inside the magnetic field, back up the other arm, back to the other side to complete the circuit. So now, once we flip on that power supply and have it set up like this, we're going to have an electric current going through a wire that is exposed to an external magnetic field. Does that make sense? All right. In the first experiment, the first part to this experiment, you're going to keep the length of wire constant. There are 6 different lengths of wire that you can plug in and out. You want to keep the length of wire in this experiment constant. What I'm going to suggest to you is that you use the longest wire. There's 6 different lengths of wire. If you use the longest one, then you're going to notice the biggest difference from trial to trial in your data. And that makes it a little bit easier to do an analysis when you notice a difference from one trial to the next. So use the longest wire. It's not critical that you do, but it just makes it a little bit easier to do your analysis if you do. So that's my suggestion, use the longest wire. Now, we're going to manipulate the current here. You're going to change the current. And the way you're going to do that is by adjusting a knob that's on the right-hand side of this power supply. Give you a little bit more detail on this, okay? Put the wire, again, the longest wire probably in between the magnets. Make sure it's not touching the magnets. Make sure it's not touching the bottom or the sides, but yet make sure it's in there. Okay, I went in there at one point in the last class, and one of the groups had the wire not touching the sides of the bottom, but it was only kind of half between the magnetic field. It was partly out of the magnetic field, kind of up above the magnetic field. You want it to be in, okay? You want it to be fully in the magnetic field, but you don't want it to be touching the sides or touching the bottom. So you're going to have to play with it a little bit in order to make sure that all of those conditions are met. There's 2 knobs on the right-hand side of this power supply. You're going to turn the top one, the voltage knob, as far to the right as it will go. Okay, as far to the right as it will go. And then you're going to turn the current knob as far to the left as it will go. As you're adjusting the current, you're going to turn the current knob on the bottom ever so slightly to the right. So you're going to turn it up a little bit. And as you do that, you're going to see a reading on the right-hand side of this power supply that increases. Don't worry about this number right here. Okay, forget about it. Doesn't matter what that number right there is. Okay, we're manipulating the current here while keeping the length of the wire constant. Ultimately, in the first experiment, we want to find the effect of manipulating the current on the magnetic force. So of course, everything else has got to be kept constant, except current and the magnetic force. Now, how is it exactly that we're going to measure the magnetic force? Current's easy. We just read it right off the power supply. How do we measure the magnetic force? Well, we have kind of an ingenious little way to do that. We use this scale that measures to the nearest 100th of a gram. What I want you to do when you start the experiment, after you turn the scale on, is put the magnet put the magnet on the scale, and then press the tare button, press the 0 button, so that you trick the scale into thinking that that magnet doesn't weigh anything. It should read 0 with the magnet on it. Now, once you put the wire, the printed circuit, in between that magnetic field and you turn the current on, there should be a force on that wire. Right, we learned about that yesterday. The magnetic force on the wire that carries a current through the external magnetic field. There should be a force on the wire. Now, if the magnets apply a force on the wire, then the wire should apply an equal and opposite force on the magnets. Well, if it pushes the magnets down, the scale is going to start reading something. It's like you go up to a bathroom scale, okay? Your little brother's on the bathroom scale. Oh, Dad, I weigh 38 pounds. And you go up behind him and you kind of put your foot on it and he says, oh, Dad, I weigh 43 pounds. Right? Because you're pushing down on the scale. That's what's happening here. Okay, the wire should push down on these magnets. It's not touching, but the magnetic force should push down on those magnets and cause the scale to read something. It's tricking the scale into thinking there's more mass there than there really is. Does that make sense? So you're going to record, of course, the length of wire that you use, which is going to remain constant through the whole first experiment. You're going to record the value of your first current, and then you're going to record the value of the mass. I put that in quotation marks because it's not really mass, right? It's just the scale thinks it's mass. The one that corresponds to the current. Then you're going to change the current, okay, and you're going to see how the mass responds to that. Change the current again, and so on and so on and so on. You do that 10 times so that you get 10 different currents. But don't go over 2 amps. Okay, if you find yourself after 5 trials, you're all the way up to 2 amps already, and you're like, well, what do I do now? Because I don't have any room to go up any higher. We'll just go down. If you went 0.2, 0.4, 0.6, 0.8, whatever, and you need some more data points, well, then go down to 0.75 or 0.7 or 0.65 or go something in between one of the trials that you've already taken. Bottom line is don't go over 2 amps. That's the first experiment. Manipulate the current, keep the length of wire constant. Try to find what effect manipulating the current has on the magnetic force. Second experiment, this time we're going to keep the current constant. I would suggest using a current of around 1 amp for that. But if you're having a hard time getting it adjusted to exactly 1 amp, maybe you get it 0.98 amps. That's fine. 1.04 amps, that's fine. It doesn't matter exactly what it is, as long as you record exactly what it is. If you got exactly 1 amp, that's great. Write it down. If you got 1.04 amps, that's great. That's fine. Just write down 1.04, not 1.00. Same setup as we had before, although this time we're changing not the current, we're changing the length of wire exposed to that magnetic field. So you're actually going to unplug that little printed circuit cartridge and then plug a new one in. Now, it's important here as you do that, in between each trial, you turn the power supply off. A little switch, on-off switch. Turn it off. You're not going to electrocute yourself if you forget to turn it off and touch the bare wire. You won't hurt yourself. You won't hurt the apparatus. But as a matter of good habit, when we're touching bare wire, it's probably good not to have the power turned on, just as a matter of general safety. What I also want you to do in between each trial, while the power supply is turned off, zero it. You don't have to do that for the first experiment. All you're doing is turning up the knob, a little bit further, a little bit further, a little bit further. But every time you turn off that power supply, and you're going to turn it off every time you unplug one of those, then I want you to zero it. That make sense? All right, so what are you going to do here? Well, it doesn't really matter which wire you start off with, but it's probably going to be the longest wire because you've got that in there from the first experiment already, right? You got the current set at 1 amp. Write down whatever your current is. Write down whatever your quotation marks mass is as a result of that wire that carries that 1 amp current going through there. Then you're going to flip off the power supply. Then you're going to replace it with another one of these little cartridges. Flip it off, replace it with another one of these little cartridges, and so on. There's only 6 of them total, so you're only going to have 6 data points for your second experiment. That's all that we have. Record the current, roughly 1 amp. Record the wire length. Record the mass. that goes with that wire length, change the wire length, see how the mass responds to that, so on and so on and so on. Finish that off. You got 2 data tables. Now you got to create 2 analysis tables. Your analysis tables will consist of, well, that's what you already wrote down for data, but your analysis will have 1 additional column in it, magnetic force. Now, how are we going to find the value of magnetic force? Here's kind of the neat and genius part of this whole deal. The scale was tricked into thinking that there was a mass on it. The scale was tricked into thinking every time the wire applied a magnetic force and pushed down on those magnets that there was a mass that made it heavier. Well, the scale is calibrated according to gravity. So that means if it's tricked into thinking that there's a mass of 0.15 grams, then it's tricked into thinking there's a force of gravity of 0.15 grams times 9.81. So what we're going to do here to find the magnetic force is simply multiply the mass in kilograms, right? It's grams on the scale. You're going to divide it by 1,000, convert it to kilograms, multiply it by 9.81. Done. And of course, it's the same deal over here. What I would suggest you do is do it on your spreadsheet. Type all these values of current and mass into your spreadsheet, and then just create a formula on the spreadsheet to calculate magnetic force. Copy that formula. Do it once. Save yourself the bother of punching every single one of them into your calculator. As you come back into the room and are working on the activity, if you're having trouble with that, you're not sure how to do that, I can help you with that. What's going to come next? What do you think's next? What's always next after a data table? Graph, yeah. In fact, we're going to have 2 of them this time because we have 2 analysis tables, 2 little experiments. The first graph is going to be force versus current. It should give me a nice straight line. Okay, plot that line in best fit in Google Sheets. Have it display the value of the slope. And then what I want you to do is determine what the slope represents. Okay, figure out what the slope means, figure out the value, and then use that along with the length of wire, which was the longest wire, and it was held constant through this experiment. Determine what the value of the magnetic field was. Like, see what the value of the magnetic field actually is. And we've done this a couple of times before, but it's been a while. The equation that describes this graph is y equals mx plus b. Always describes a straight line graph. The y-axis, in this case, is force. M is the slope. The x-axis is current. And there will be no y-intercept, at least not in any measurable, not any appreciable y-intercept here. Now we've got to come up with an equation that appears on our data sheet that has both F and I in it. Well, we know what that is because we learned it yesterday. F is equal to ILB. Just change the order of this a little bit so it matches up with this one. F is equal to, what do we got here? LB I. Same thing, isn't it? Is that the same thing? Yeah, it is. Cross off F because it appears in both. Cross off I because it appears in both. Look what we can do. The slope of that graph is equal to L times B. Now the slope of the graph, Google Sheets is going to spit out for me. The length of the wire I recorded in my first data table. I can calculate the magnetic field that we use there. I'm going to do something pretty similar in my second experiment, except my graph isn't going to be force versus current. My second experiment is going to be force versus wire length. It's also going to be a straight line. It's also represented by y equals mx plus b because every straight line graph is. Y is force. M is slope. X is the length of the wire. Won't be any y-intercept, not appreciable anyways. Equation on our data sheet that has those same 2 variables. F is equal to ILB. Let's change the order of it a little bit. F is equal to IBL. We don't need to change the order of it like that. It just makes it a little bit easier to see. Cross off F because it appears in both. L because it appears in both. And we're left with, in this case, the slope is equal to I times B. Let's find the value of the magnetic field now. The slope, Google Sheets spits out for me. The current was about 1 amp, right? Whatever you recorded it to be. Find the value of the magnetic field. What should you notice about the magnetic field that you calculated in the second experiment as compared to the magnetic field in the first experiment? They should be the same. We didn't change that, right? So it should be the same value. Now, what value do you think it should be? Anybody have any idea? We talked about differing magnitudes of magnetic fields on the second day of class. If you get a value that's 10 to the 4 Tesla, you're wrong. The strongest human-made magnet ever has been about 40 Tesla, 10 to the 1. If you get 10 to the 4, you're wrong. If you get 10 to the minus 6, you're wrong. The Earth's magnetic field is 10 to the minus 5, and these are going to be definitely stronger than the Earth's magnetic field. Bar magnets were typically 10 to the minus 2 Tesla, and that's probably what you should expect to get here, is somewhere in the 10 to the minus 2 range. Okay? Could be 2 times 10 to the minus 2, it could be 8 times 10 to the minus 2, but it's not going to be 10 to the minus 5, and it's not going to be 10 to the positive 1. Yep. Finally, what do you got to hand in? This one's easier than the other ones we've done. Data, which you've got a copy of the data table in front of you right now. You're just going to have to copy that over into Google Sheets, or Google Docs, I should say. Data analysis, which includes your table that I showed you and that you have a copy of. It also includes the 2 graphs, which Google Sheets is going to plot for you. Your conclusion, which is basically going to say, let's say you got a magnetic field of 0.3 and 0.03 in the first one and 0.04 in the second one. Say the magnetic field is somewhere between 0.03 Tesla and 0.04 Tesla. This is how I know. Okay, this is how I know what its value is. Okay, you might want to make a comment about how close the range is or how far away the range is. Finally, sources of error. The closer those are together, the less your sources of error, how do I say this? They don't need to be quite as strong, right? If they're really good values that really agree with each other, then things went pretty good. If you get a big difference between your 2 magnetic fields, then your sources of error need to be a little bit stronger, right? Bottom line is, okay, if there's anything that jumps out at you as being a problem with the procedure or time management or the materials or anything like that, then draw attention to that. Okay? And provide me with a way of maybe fixing it next time. Yeah, Josh? You don't have to do a percent error calculation. No. Certainly you can, and that might be something that you want to look at with in your analysis. But I'm not going to say that's mandatory this time. We don't necessarily have to quantitatively compare those 2 numbers. Your conclusion is not so much how far apart are they. Your conclusion is it's somewhere in this range. Does that make sense? So percent error calculation would certainly not be wrong, but it's not required for this.